I'm Simply Positive, and today we begin lesson 2 of category theory. And we actually begin part 2 of category theory, which is our introduction into standardized category theory. So, without further ado, let's get started. We covered, here's going to be our summary. So, we covered the prerequisites of category theory, which were knowing what a definition was, knowing what a mapping was, and knowing what the tag system was. And for those of you kind of coming um, in straight into video 3, a definition is we define it as a term followed by a colon, followed by either a mapping or a description. A mapping is a relation from thing 1 to thing 2 via an arrow. And for our tag system, we said that we would have a tag to represent the type of thing that we're talking about, followed by a name. Sorry, I got confused for a second. Okay. And then we then went on to base category theory, where we defined, well, what is category theory? It is a framework for defining and describing relations. We said a category is a universe where it houses our objects. An object is a placeholder of acceptable values, and that an element is that specific value, and that categories house objects which house elements, and that the fourth thing of category theory was mappings, which again, from the prerequisite of mapping, relates one thing to another. It's an arrow, right? And that there are three different types of mappings. There are functions slash morphisms, which relate objects to objects. So this is just one way of using the tag system of showing a. So here is an example of a definition where we define the function f. We define the function f as relating object A to object B. That's just one example of a definition and a mapping. We have functors, which relate category to category, right? And then we have natural transformations, which relate functors to functors. Okay. We then defined what a commutative diagram was. There it is. Which was just the diagram of the mappings and objects in our category. And we defined a process for creating our commutative diagram, which consists of the definition and mapping phase, standardization, and proof, which we won't cover probably until a later series. And again, definition and mapping, you're just making your definitions and you're making your mappings. Standardization is where you actually give the specific name of the thing that you just did, which we're going to talk about really soon. But before we do that, let's get on with today's lesson, which are going to cover the 6 rules of category theory. So there are really 3 axiom rules and more like 3 perspectives, if you want to call it that. So the 3 axiom rules are identity, composition, and association. And what that means is no matter what category, no matter what relation that you decide to make, all of these must be true. So, no matter the category, your identity rule must be true, your composition rule must be true, and your association rule must be true. When it comes to the 3 perspectives, we have isomorphism, equality, and duality. And when I say that they're perspectives, they need not necessarily be true all the time. And they are more like, you should treat them more like perspectives to view your category theory from. So let's start with the 3 axioms. We have the identity rule, which states that for every thing, there is a mapping from that thing that points back to that thing. So, for example, for let's say we have the object A, right? In a random category. Well, technically, because we have object A, we technically have to have, or at least have to imagine, that there is a identity function that points a. So I'm going to put identity function. Let's say that this is identity function f that points a back to itself. Okay? So for everything in our category, this is always going to be true. You don't always have to explicitly write this, but you should imagine that this is always true for everything in the category and including the category itself. For the composition rule, when you have multiple paths, you can combine the paths into a shortcut, and the order matters. So what do I mean by this? So let's say we now have object A leads to object through F leads to object B, which then through G leads to object C, and then through H leads to object D, right? So we have 3 paths. So from A to B, it goes through F. From B to C, it goes through G. From C to D, it goes through H, right? And remember, F, G, and H are morphisms, or their functions, right? So according to composition, technically, you can make a shortcut from A to D, so from object A to object D through the composition of F, G, and H. That reads like so. So you can group mappings together uh, as long as they logically connect from one object to another. Which leads us to our next thing, which is association, which means the order of the composition matters, but not necessarily the grouping. Okay. So remember how I have FGH? Well, technically, you can do a composition of F and G and then run that result through H, or you can do F and then the composition of G then H, right? These are functionally the same. So, in other words, I can do F and G in one step and then do H, or I can do F and then do G and H in one step. I hope that makes sense. So, those are the three axioms. And now we get on to the three perspectives, which again, they don't always have to be true for every situation when you're making your category. So we have isomorphism, which states that if there is a relation from one object or one thing to another, and then another relation from, so that goes back, the relation is an isomorphism, and the two objects are isomorphs. What do I mean by this? So let's say we had an object, right, that went from A. You know what? Let's say we had a category, right? A category A that went from A to category B, right? And we had F. Do you remember what F needs to be to relate category to category? F is a functor, right? So we have functor F that relates category A to category B. Now let's say that we have a functor G which goes directly back from category B back to category A. This would be considered an isomorphism because there is no gain or loss of information. They map to and back from each other perfectly. Okay? Now, I say that this is a perspective because this immediately leads into the next rule, which is equality. So it's the same as isomorphism, but instead of saying that the two things are isomorphs, they are instead functionally equal. So you literally have that same setup where you have a relation from A to B and then another relation back from B to A. But instead of concluding that A and B are isomorphs, you conclude that A is functionally equal to B, meaning that A and B, for all intents and purposes, are the same type of thing. Okay? And a lot of the times when you apply the equality rule, there may be gain or loss of information. I'm just going to put plus minus. Um, That's the equality rule. And then the next rule is duality, which is for every given category that you make, imagine a category where everything is flipped, right? And again, you don't have to explicitly write this. It's just sort of good practice to keep these things in mind, right? So, category A, or you know what? Let's change it up again. Let's say functor A instead. And functor A relates through F to functor B. Now, what does F need to be in order to relate functor to functor? Right, it needs to be a natural transformation. Okay? Now, according to duality, there then let's say that this was all in um within a category X, right? According to duality, there must then exist a category X opposite where instead of F relating A to B, there is an F opposite. So it looks something like this. So now instead there is an F opposite that relates B back to A. So it's literally just you flip it. Okay? And that's pretty much it for today's lesson. Today's lesson's pretty light. It just covers the 6 rules of category theory, which were identity, composition, association, isomorphism, equality, and duality. And so now up to this point, we have covered a pretty large bit of category theory. We covered the prerequisites, which again are knowing how to make a definition, knowing how to make a mapping, and knowing the tag system that we are using. You can make up your own tag system. It's just I recommend using a tag system because the notation for category theory is complex and you shouldn't waste a lot of time trying to memorize it. And then we went on to base category theory, which was, well, what is category theory? It's a framework. We have our things of category theory, which were categories, objects, elements, and mappings. And then we had our 3 different types of mappings, morphisms slash functions, functors, and natural transformations. Okay. And then we went over what a commutative diagram was, as well as the design process for category theory, which is you make your definitions and your mappings first, and then you standardize. So for example, you can make a relation from A back to itself, but then through standardization, you know that such a relation would be called a identity function. It'd be called an identity function, right? And then finally, we have proof. So I hope that was clear for today. That's gonna wrap up today's lesson on category theory. I hope you join me next time for the next lesson where we're going to be going over morphisms. And I have to say that if you get morphisms, you're pretty much set on category theory. Their morphisms is by far the most important part of category theory simply because of just how complicated the relations can be. So, you know, before you move on to the next lesson, really take some time to get these first 3 videos down. And honestly, once you get this next video, you're pretty much done, if I'm being honest. Uh Thank you for your time. I am Simply Positive, and I hope to see you again in the next video. Take care.